All right, so let's get started on our last set of notes related to derivatives and limits, and we're going to learn how to apply derivatives, or more importantly, how they're used to understand certain things about functions that we've looked at in the past, but now we can get into more detail because we know how to find a derivative, and we're going to talk about what it means to understand the value of the derivative at different points on a graph. So, take a second and write a definition of a derivative in your own words, and then pause the video and come on back and see if your definition or definitions line up with what we write. Okay, so the way to think about a derivative is one of two ways. There's sort of a more formal way, which is the instantaneous rate of change. Instantaneous of change of a function, meaning that's the rate of change at one single point on a function. And typically we're talking about functions that are nonlinear, because on a linear function the rate of change is constant anywhere on the graph. But in nonlinear functions, the rate of change changes depending on what x value you're looking at. Another way you can think about it is the slope of, or the slope at a point tangent to the function, meaning it just touches at one point. They're really saying the same thing, but that's the idea. We're thinking about the rate of change at a particular point on a nonlinear function. So just a little review from last class. We're going to find the derivative of the next three functions here, and they are all ready for us to use the power rule. So we're going to go ahead and find the derivative of each of these. So we'll say h prime of x equals, and then we'll go term by term and use the power rule. So the x cubed, the cubed comes out front to be a coefficient, and the power of x drops by 1, so 3x squared. We do the same thing for the next term. That squared, that power of 2, comes out and multiplies times the 2 that's already there, and then x squared drops to x to the 1. On the next term, the power is 1, and the number that's in front is negative 1. So 1 times negative 1 is just negative 1. And then x drops to the power of 0, but we really don't write that. Anything to the power of 0 is just 1, so we'll just leave that like this. Now you'll notice right here that we have this constant. Keep in mind that the derivative of a constant is 0. And so that term just disappears. So you notice every term goes down by 1 power. So the cubed becomes a squared, the squared becomes a power of 1, the power of 1 becomes a power of 0, meaning that x, or the variable, disappears. Okay, so let's do the next one then. M prime of x. Again, bring that 3 out front and multiply it times the negative 5, so negative 15, and then drop the power of 3 to 2. For the next term, the negative 12x, that's a power of 1, so it's just going to be minus 12, and the x disappears. And then again, the derivative of this constant is 0, and we are done finding our derivative. So just keep in mind, every time you do this, the power should drop by 1 for every term. Okay, so for this last one, instead of x's, we have r as our independent variable, our input. And so we have a familiar formula, pi r squared. Maybe you remember it, maybe you don't. But pi r squared is the formula for area of a circle. And so we want to find the derivative, and then we'll look for something interesting or familiar about the derivative of this. So we're going to say f prime of r. That indicates this derivative of f of r. And then this 2 is going to come out and become a coefficient that joins with the existing coefficient, pi. So it's 2 pi. And then r squared just drops to a power of 1. All right, so take a look at that and see if you remember what 2 pi r represents. If you don't remember, 2 pi r is the circumference of a circle. And so this is something really cool when we talk about area and circumference of a curved shape, like a circle. The derivative of the area is the circumference. So these formulas are related, and if you remember back to geometry, when you learned like surface area and then volume, those formulas are derivatives of each other, or antiderivatives, depending on which direction you go. But they're related. They don't come from nowhere. Okay, so here's where we're going to talk about how we use the derivative to help us understand some things. So position, velocity, acceleration. Most of the time you're going to be given something where you're told, hey, this function represents the position of an object at a given point in time. So you might see it represented a couple of ways. You might see s of t or h of t. Usually this is because it's like height as a function of time. S would be position. You might also see y of t, which would also be like height or position. But the idea is the first equation that you're looking at represents the position. If you want to represent the velocity using that position function, the velocity is the rate of change in the position over time. So, aka the derivative. Derivative of position. So the velocity is going to equal the derivative of whatever our position function was. So s of t or h of t, that'd be h prime, s prime. But the main point is it's the derivative of position. So let's write that here. Derivative of position. Get this out. Acceleration, well, going back to velocity. Velocity is basically like the speed, right? How fast is something moving? Acceleration is a little bit different. Acceleration is the rate of change of the velocity. So how fast is the speed changing over time? So acceleration is a little bit different. You'll see it most of the time represented as a of t, that's for acceleration, v of t for velocity, pretty intuitive. And so a of t would be the derivative, rate of change, of velocity. Derivative of velocity. So derivative v prime of t. Now, if we say we're taking the derivative of velocity, well, velocity is the derivative of position. So another way we could say this is the double derivative of the position, or the second derivative. So acceleration is the second derivative of position. And then velocity is the first derivative of position. And so what we're going to do is we're going to use this in a couple of word problems. And you just have to pay attention to what you're given, whether you're given the position or the velocity, and then what they're asking you to find to decide if you're just doing one derivative or two derivatives. Okay, so a soccer ball is kicked straight up in the air. The height of the ball, position, so when you see height, we're talking about position, is defined by this function. So we got h of t, where time is given in seconds and height is given in feet. And it's good to notice these things so that when we find our answers, if our answer is a time value, we remember to label it as seconds. And if it's a height value, we should be labeling it in feet. All right, so A first says, find the expression for the instantaneous velocity of the ball at any point in time. So all we're doing here is take the derivative. So I'm going to go ahead and take the derivative. And so I'm going to say the velocity, which is the derivative of the height function. And then I'm just going to go term by term. 55t becomes 55. And negative 16t squared, I'm going to bring that power of 2 out. Multiply it times negative 16 is minus 32t. All right, so this is the function that represents the velocity at any time. Problem B says, hey, find the time. Okay, so let's key in on that. We're finding the time when the ball reaches the maximum height. So if you think about a ball being starting on the ground, a little soccer ball, and then it gets kicked up, and then it comes right back down. The time when the ball reaches its maximum height, we're going to use the fact that at the top there, the velocity is going to equal 0. When we go to when it's moving up, it's got a velocity. When it's moving down, it's got a velocity. But right when it turns from up to down, the velocity equals 0. So we're going to find the time when v of t equals 0. So we have our v of t function, and we're going to set it equal to 0. So I'm going to say 0 equals 55 minus 32t. And then we'll just do this algebra style. Add the 32t, divide by 32. And then when you put that in your calculator, we get the time is, if we round it to the nearest hundredth, we'll say 1.72 seconds. So the ball's kicked up at 1.72 seconds. That's when it starts turning and coming back down. The third question here, part C, says find the maximum height. So this time we're not trying to find a time anymore. We're finding a height. So if we're meant to find a height, then we should be using the function that represents height. So when we look at that function, h of t equals 55t minus 16t squared, we know when the ball reaches its height. We're going to use that to figure out what the height is. So we're going to plug in the time we just found, which was 1.72 seconds, and just solve, because that's going to tell us how high the ball is at that time. And then, let's see, that t needs to be 1.72. Let me fix that. 1.72 minus 16 times 1.72 squared. Okay, so once you put all that into your calculator, our height at 1.72 seconds equals 47.27. And then again, because we're talking about height, we need to label this with the right unit of measure, which is feet. All right, so that's one of the most common applications, is where we can figure out when does the maximum happen, solving for the independent variable, and then use that value and plug it into the original position or height function to find out what is the height at that particular time. So we'll do this last one. Acceleration is the rate of change of velocity, which we discussed. The velocity in meters per second of a particle moving along a straight line is given by this function. So here we're not given the position, we're actually given the velocity. So we already have the velocity function where t is time in seconds. We're supposed to find the acceleration of the particle in meters per second squared after 5 seconds. So in order to figure out the acceleration as a function of time is the derivative of our velocity function. So we just have to find the derivative of our velocity function first. And then it wants to know what's the acceleration at 5 seconds. So let's go ahead and find our derivative first. So 3t squared, you bring out that power, we get 6t. For the second term, that's a power of 1. Bring that out, minus 6. The plus 5 constant disappears. So we found the derivative. This is our acceleration function. Now what we're going to do is say, what's our acceleration at 5 seconds when time equals 5? So I'm going to say a of 5 equals, and then I'm just going to plug in. So it's going to be 6 times 5 minus 6. So at 5 seconds, we'll be able to tell what our acceleration is. 30 minus 6 is 24. And then acceleration is measured in meters per second squared. So anytime we're doing acceleration, it'd be meters or feet or whatever per second squared. So that's how we kind of use the derivative to help, and this should help you with your last assignment.